Hello friends, dear learners and my dear student. First of all, I take an opportunity to welcome you on the lecture Ultraviolet and Visible Spectrophotometry. Student, I am Dr. S.R. Labhade, working as an Associate Professor in the Department of Chemistry. Student, in previous lecture we discussed laws of photometric analysis, that is Lambert's law and Beer's law, as well as we discussed the deviation from the Beer's law. Based on the photometric law, we also solve some numericals. In today's lecture, we also solve the numericals based on the laws of photometric analysis. Therefore, problem first. A colored solution when placed in light path, when placed in a light path, shows transmittance 0.4. What will be the transmittance of same solution when path length is doubled? Here, a colored solution when placed in light path shows a transmittance 0.4. What will be the transmittance of same solution when path length is doubled? Student, we know that transmittance decreases exponentially with the concentration. Transmittance decreases exponentially with the path length. That means here, when the path length is double, absorbance is not becomes half or is not become equal to double. That means here we have to find out the absorbance at this transmittance. Then we have to multiply that absorbance with 2. Then we have to find out the transmittance for that second absorbance. Therefore, here A is equal to minus log T. Here A is equal to minus log of 0.4. Therefore, A is equal to 0.398. This is a absorbance. When path length is double, then A is equal to 2 into A. Therefore, A is equal to 2 into 0.398 and which is equal to 0.796. Therefore, here we have to find out the transmittance for this absorbers. Therefore, A is equal to minus log T and therefore T is equal to antilog of minus A, that is 0.796, and finally this value is equal to 0.16 transmittance. Therefore, transmittance is decreases to 0.16. Here, as path length is double, here transmittance is equal to 0.16. It indicates that transmittance is not directly proportional to path length or it is not inversely proportional to path length. Transmitter changes exponentially with increasing path length. Student, now second problem. A colored solution. Second problem. A colored solution having concentration 0.005 moles in a 4.0 centimeter scale shows at of 0.25. What will be the transmittance of same solution in a 1.0 centimeter path length cell? Similar to earlier problem here, absorbance is given in 4 centimeter cell. We have to find out the transmittance of same solution when it is placed in 1 centimeter cell. Therefore, initially we can have this relation. We have to find out the absorbance in 1 centimeter cell. That means it can be reduced to 1/4, because here when path length is 4 centimeter, absorbance is this much, how much? 0.25, and when path length changes to 1/4, absorbance also changes to 1/4. That means here, in another way we can solve this problem. A is equal to epsilon into B into C. Therefore here epsilon is equal to A upon B into C. Therefore A is 0.25 divided by 4.0 into 0.005. Therefore this value is 12.5 liter per mole per centimeter. Now here when B is equal to 1 and C is equal to same, then we can find out A is equal to epsilon into B into C. Therefore epsilon is 12.5 into B is 1.0 into C is 0.05, and this value equal to 0.0625. That means if we divide 0.25 then by 4, then we have this value. Therefore this is a new absorbance, and now we have a relation, that is A is equal to minus log T, and therefore T is equal to antilog of minus A, and antilog of minus A, that is minus 0.0625, and finally this value is equal to 0.866. This is a transmittance. Therefore here in a 1 centimeter cell transmittance is increases, and here in 1 centimeter cell absorbance decreases to 1/4. But we can find out it in this fashion. Student, now we solve next problem, that is based on the calculation of absorbance when path length and the concentration is doubled. Therefore here third problem, a colored solution transmits 87.5% of the incident light What will be the absorbance of the solution when path length and concentration both are doubled. In this case, only the transmittance of solution is given, and we have to find out the absorbance when path length and concentration of the solution is doubled. Therefore, here at this transmittance, here colored solution transmits 87.5% of incident light. Therefore, out of 100, 87.5% is transmitted. Therefore, A is equal to, in this case, A is equal to log of P0 upon P, which is equal to log of P0 is 100 divided by 87.5, which is equal to log of 1.143, and this value is equal to 0.058. That means this is the absorbance. Now here, when absorbance and concentration both are double, when path length and concentration both are double, then that will directly affect the absorbance. This is the absorbance. A is equal to 0.0. That means when epsilon into B into C, that is equal to this absorbance, 0.058. This is a absorbance. Therefore, when path length, that means epsilon is constant, path length is double, concentration is double, then we have to find out this absorbance. Therefore, which is equal to 0.058 into 2B into 2C divided by epsilon. Again here is epsilon into B into C. Here this will be get cancelled with each other. Then we have to simply multiply this 0.058 into 4, and which is equal to 0.232. This is the absorbance. That means here, when path length and concentration both are double, then absorbance increases to 4 times. Because if path length is double, absorbance is double, concentration is double, then absorbance is double. Therefore, here this value increases to 4 times when absorbance and path length both are doubled. When concentration and path length both are doubled. Student, next problem. Number 4. A 6.44 into 10 raised to minus 4 moles per liter of complex solution has T is equal to 0.34 in a 1 centimeter cell. What is the concentration of the complex of the cell complex that has T is equal to 0.516 in 0.5 centimeter cell. In this case, transmittance of this solution is given. Transmittance of 6.44 into 10 raised to minus 4 moles per liter of complex solution is 0.34 in a 1 centimeter cell. We have to find out the concentration of complex, which shows a transmittance this much in a 0.5 centimeter cell. Now here path length reduces to half, and here transmittance increases. Therefore, we have to find out the concentration of complex, which transmits 0.516% of light. Which transmits this much light. Therefore, here first of all, T is equal to 0.34. This 0.34 we can use for calculation of absorbance. Log minus log T. Therefore, A is equal to minus log of 0.34 and which is equal to 0.4685. Here this is a absorbance of solution which having transmittance this much. Epsilon, that is a molar absorptivity, that does not affect, that remains same for the similar type of material. Therefore from this we can find out the value of epsilon. Here epsilon is equal to capital A upon B into C. Therefore here absorbance is 0.4685 divided by B is 1 centimeter into C 6.44 into 10 raised to minus 4 moles per liter, and finally this value is equal to 7 to 7.5 liter per mole per centimeter. Now here we have value of epsilon. Now from this, for this second solution we have transmittance. Therefore here again T is equal to 0.516. Therefore again A is equal to minus log T. Therefore A is equal to minus log of 0.516 and this absorbance is equal to 0.2874. This is a absorbance of that solution which transmits this much amount of radiant power. Therefore here we can find out the concentration. We have value of epsilon, we have absorbance. Therefore A is equal to epsilon into B into C. Now C is equal to capital A upon epsilon into B, and therefore here capital A is 0.2874 divided by 7 to 7.5 into 0.5. Now B changes to half, that is 0.5 centimeter. And therefore when we solve this, we have concentration 7.899 into 10 raised to minus 4 moles per liter. In this way we can find out the concentration of the complex solution. Now we solve the problem based on the calculation of absorptivity as well as calculation of concentration based on the absorptivity. Therefore problem number 5. Here the molar absorptivity of a complex is 50 liter per mole per centimeter at 745 nanometer. We have to find out, determine the transmittance when light of this wavelength passes through complex having concentration 0.1 moles per liter and path length of 10 millimeter. In this case, molar absorptivity is given. Value of epsilon at path length is given. We have to find out the transmittance. Therefore, in this case, here when B is equal to 10 mm means is equal to 1 centimeter and epsilon that is equal to 50 liter per mole per centimeter. Therefore, according to Lambert's Bayes law, A is equal to epsilon into B into C. Here A is equal to epsilon, that is 50 into P is 1 centimeter into C is 0.1. When we calculate this, we have this value equal to 5. Therefore, here absorbance is 5. We have to find out the transmittance. Therefore, this value of absorbance we can utilize for calculation of transmittance. And A is equal to minus log T. Therefore, T is equal to antilog of minus A. And here, antilog of minus 5.0 and which is equal to 10 raised to minus 5. This is a transmittance, or this is a 0.0005 is the transmittance. That means very small amount of light is transmitted through that solution, because here absorbance is 5. Here we can calculate the transmittance when we know only the molar absorptivity, and we can also utilize molar absorptivity for determination of concentration of substance. Therefore, next problem, the molar absorptivity of a dye solution at 550 nanometer is 2.0 into 10 raised to 4 liter per mole per centimeter. Calculate the concentration of same solution, same dye, which shows transmittance of 0.72 in a 1.5 centimeter say at this wavelength. Now in this case, the molar absorptivity of dye at this wavelength is given 2.0 into 10 raised to 4. Molar absorptivity is in the order of 10 raised to 3 to 10 raised to 4, and it is expressed in liter per mole per centimeter. Here molar absorptivity of dye solution at this wavelength is given. Again we have given a transmittance of same dye solution in a 1.5 centimeter cell. We have to utilize these three factors for determination of concentration of dye. Therefore, concentration that can be determined by using this equation, epsilon into B into C. Here we know the value of epsilon, we know value of B, we have to find out value of C, but here we also calculate the value of A. And therefore, A is equal to minus log T. Therefore, T is equal to 0.72. Therefore, A is equal to minus log of 0.72, and which is equal to 0.1427. Here we have value 0.1427 into epsilon is 2.0. Therefore, C is equal to 0.1427 divided by epsilon, that is 2.0 into 10 raised to 4 into path length 1.5 centimeter. When we calculate this value is equal to 4.75 into 10 raised to minus 6 moles per liter. In this way, we can find the concentration of the dye solution or any other solution whose absorptivity is given and transmittance is given.